In this video I want to talk about definite integral and how it's related to the area under a curve, and we'll use and define Riemann sums as a way to define our definite integrals. So I want to start with the idea of area under a curve. We've already talked about that, or hopefully you've seen that before at some place. And one of the strategies we looked at is that we could take the area under the curve and divide it into rectangles. So we could keep making rectangles. Alright, and we have to figure out how we're going to define the height of these, and I'll talk about that in a moment, because right now it's not a rectangle, right? It's got a curved top. But for example, here we could define the rectangle using the left endpoint, which gives us an overestimate, or we could define it using the right endpoint, and in this case that would give us an underestimate. So there's more than one way to define where we're going to cut off the top of our rectangle. So we actually have a rectangle and not something that looks sort of like a trapezoid. So let's think about then what the width of these rectangles would be. So if we had n of these rectangles, all right, from A to B, and let's say they were equally spaced, all right, so they all had the same width, then the width of one rectangle would be equal to the length of the interval divided by n, or the number of rectangles. All right, so if we were going from, I don't know, say 0 to 10, and we had 10 rectangles, then the length of each of these sub-intervals would be equal to 1. And we use the notation delta x to denote the width of each of these rectangles. So the width here is delta x, and this is delta x, and so on. So then the endpoints of our rectangles, so here clearly the left endpoint would be A, and then here I would have A plus delta x at this point, and then here I would have A plus 2 delta x. And when I get out to B, B would be A plus n times delta x. In other words, since each of these is the length of the interval divided by n, then I take n of those and I just end up with, and add that to A, I end up with B. I end up with the length of the interval added to A, and that gives me B. So here then, of course, I would have A plus n minus 1 times delta x, and so on. So the point is we can define the endpoints of each of these rectangles in terms of A and the number of delta x's, which is the width of each rectangle. So that gives us the endpoints, so we can think about that in terms of the widths of these rectangles. But what about the heights of the rectangles? So that's what I was just talking about a little bit before. So one way to define the height of the rectangle is I could take the function value at m sub I, which is the minimum function value in the ith rectangle. All right, so let me talk a little bit more about what I mean by that. So in this case here, so if we are in the first rectangle, so this would be this point right here would be f of m1. All right, it's the minimum function value in this first rectangle. This right here would be f of m2, and then when we get to the other side, now this would be f of mn, right? It's the smallest function value in the nth rectangle. So likewise then, we could define f to be, we could find f of capital M, and this would be the max function value in the ith rectangle. All right. So again, here this would be f of big M1. Turns out that this f of little m1 would also be f of big M2, because this is the largest function value in this second one. Over here, of course, we would have f of big M n. All right. So why am I defining two of these, right? So we would end up with, again, if we look at these, I'll use green for the lower. So I could have a rectangle like this. I could have a rectangle here, and all of these use the smallest function value in that interval, where I could use, if I use the largest, I would get different rectangles. That would be an overestimate. All right. So we want to use these different heights, this being the smallest height and this being the largest height of the rectangle within an interval, to define the upper and lower sums. All right. So what I want to do is say that if I take, well, let's keep this picture here. But if I take, for example, f of m1 times delta x. So does that make sense? That gives us the area of this first rectangle using the smallest height, plus f of m2, that's the smallest height in the second rectangle, times delta x times the width of the rectangle, so that gives me the area of the second rectangle. And I can keep on adding until I get out to the nth rectangle, take the smallest height in the nth rectangle and multiply it times the width of that rectangle. And there's a notation we can use rather than writing this out every time. We can use this summation notation, which many textbooks will have you do quite a bit of work in using, some rules to actually figure out these sums. I want to introduce it, but I don't think it's necessary to calculate all these by hand in order to understand what's going on. So this basically, we start with I equal to 1. So that means we're going to start here, 1, all the way up to n. That's our last one. And so I'm just going to have f of little m sub I. So what this says is we start with I equal to 1, and then we go to 2, and then we go to 3, and so on. And each time we change this index, we add. But I also have to put a delta x in here, right? So this is just taking these. In other words, for each I get the area of the ith rectangle, and then this summation notation just means we add them all up. And one way to denote this, a little bit easier, because even this is a little bit cumbersome, we're going to just call this little s of n, which is our lower sum. All right. So in a similar way, we could define the upper sum to be the sum from I equals 1 to n of f of capital M sub I times delta x, and that is denoted as capital S of n. All right, and this is our upper sum. Okay, so what we know, if we go back and look at this picture, we see that the upper sums, because they're an overestimate, will be greater than the actual area underneath the curve in here. And the lower sums will be an underestimate. So one way to say that is that little s of n is less than or equal to the actual area under the curve, which is less than or equal to big S of n. Well, as it turns out, I'm not going to prove this, but if we take the limit as n goes to infinity of little s of n, so in other words, we take the limit as n goes to infinity of the sum from I equals 1 to n of f of little m sub I delta x. So what we're saying is the number of rectangles that we're going to fit underneath this curve goes to infinity. We're going to take that limit. Turns out that that is the same as the limit as n goes to infinity of the sum from I equals 1 to n of f of big M sub I delta x, which is the limit as n goes to infinity of big S of n. All right, so it turns out that this upper sum and the lower sum, if you let the number of rectangles go to infinity, those sums are actually equal to each other. And we can see this graphically in a previous video I made. We saw this graphically in GeoGebra that they get closer and closer the larger the number of rectangles, because the error that's left gets smaller and smaller and smaller. All right, so but because by using this limit here, the lower sum and the upper sum end up being equal, then ultimately it doesn't matter which point we pick. It doesn't matter if we pick the smallest spot or the biggest spot or some arbitrary spot in between. In other words, we just need kind of a sample point somewhere in the interval, because ultimately when we take the limit, it's all going to be the same. So let's just kind of redefine our picture here very quickly. Just kind of, we had something that looked like this. All right, and we let this be A, and then we had another rectangle and a rectangle, and going on, rectangle, 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 where this was B. And I can, let me just get another color to make this a little bit easier to see. I can just pick an arbitrary, well, before I do that, let me say this, we're going to call this x0, and this will be x1, and this is x2. B will be xn, so this is xn minus 1, this is xn minus 2. All right, well, that just corresponds to what we had. We're basically saying x1 is a plus delta x, x2 is a plus 2 delta x. But I'm introducing this notation because we'll see it in a formula that I'm about to give you. But the point is, I can pick any point. So I can pick this point right here. We'll call this C1 because it's my sample point in the first interval, and we'll use that height. All right. But maybe over here, I want to use a spot that's kind of more in the middle. Let's call that C2. So I get the height of my rectangle that way there. Over here, maybe I'll pick this point here. We'll call it C sub n minus 2, since it's in the n minus second interval, and we'll use that for our height. And maybe I want to use the other side over here for, actually that would have been C sub n minus 1. This would be C sub n right here. So here, and then maybe I would use that height. So the point is, it doesn't have to always be the largest or the smallest. I can just pick any point in the subinterval. So what we end up with is that our area equals the limit as n goes to infinity of the sum from I equals 1 to n of f of c sub I times delta x, right? Where c sub I is just some point in between x sub I minus 1 and x sub I. So that's where I screwed up my notation here. So we use the I agrees with the right hand endpoint, right? So here x1 c1, x2 c2, so this should be c sub n minus 1 because that's x sub n minus 1, and then here's cn because that's xn. So it's just some point, any random point in between those two ends of our subinterval work, and that gives us the area. All right, and that's because of when we take this limit, it's going to all be the same in the long run. So that's the first thing, is it doesn't matter what point we pick in the subinterval. As it turns out, it doesn't even matter that these are all the same width. All right, so moving on to the next idea, we are going to use this notation. That's called, this double parallel lines on either side is called a norm. And the norm is going to be the width of the largest subinterval. Alright, so let's draw our picture one more time. So I have something like this. We went from A to B. Alright, and I can put one in here, I can put another one like this, I can put another one here, I might put a whole bunch in right here. Alright, they don't have to all be the same width. So this width right here would be my norm, because that is the width of the largest subinterval on the interval AB. All right. Before, when we had them all the same, then this norm was just equal to delta x or b minus a over n. Since they all had the same, then any one of them was the largest. But I just want to mention, when we're now getting into Riemann sums, this is important. This idea that we don't have to have, not only can we pick any arbitrary point in the subinterval, we don't even have to have the widths of the rectangles the same. All right. So then, to define the Riemann sum, the Riemann sum is basically what we had before, but without the stipulation that, so here, notice we have it's not just a delta x, it's a delta x sub I, all right? And the reason for that is the width of the ith rectangle will be different than, in other words, the width of the first rectangle could be different than the width of the second, or the third, or the fourth, and so on. So now the widths also have this this little index I, because they're not going to be the same everywhere, just like the heights are not going to be the same. All right, and then what we're doing with this norm is, in order to actually find the area under the curve, now we take the limit as the width of the largest subinterval goes to 0. All right. So as we put more and more, in other words, we can kind of think of this as replacing the limit as n goes to infinity, because as we put more and more rectangles in, the width of the largest rectangle, or the largest width, I should say, of any of those rectangles is going to go to 0. And so it's the limit as the width of the largest rectangle goes to 0 of the Riemann sum. So the limit of the Riemann sums is that width goes to 0. That is going to be the area. And we introduced this notation. It's the integral from a to b. So a is our lower limit, and b is the upper limit of integration of f of x dx. All right, and this is called a definite integral. Okay, and then when this limit exists, then we say that f is integrable. So this limit won't always exist, but when it exists, then we say that f is integrable, and we introduce this notation for the definite integral. So we won't actually work with, this is one of the reasons I don't think it's that important that students are able to compute these by hand, because there's a very small number of functions for which we can do this. And I think the more important thing is the ideas here, that we're taking the areas of these rectangles, and we're summing them up, and then this idea that the limit, that we take the number of rectangles in an interval and let it go to infinity. And ultimately that will give us the definite integral. Okay, so a couple last things then. First, straighten our papers out here a little. If f is continuous, then f is integrable. In fact, continuity is too strong of a condition. There's many functions that aren't continuous that are still integrable, but continuity certainly does it. All right. So if you recall, differentiability was a stronger condition than continuity. In other words, there were functions that were continuous, but they weren't differentiable. So we have that differentiability implied continuity. If it was differentiable, it was automatically continuous, but being continuous didn't necessarily mean differentiable. Here, we're going a step further and saying if it's continuous, then it's integrable, but not necessarily the other way. There are functions that were integrable that are not continuous. So integrability is actually one of the weaker conditions. Lots of functions are integrable. Not so many are differentiable, at least not at every point in their domain. Okay. Finally, I want to just talk about the relationship between area, since that's what we started off with. We started off looking at this idea of area. As it turns out, it's this definite integral equals the area only if f is greater than or equal to 0. So, for example, we could look at the definite integral from -2 to 1 of 2x dx. So one way to think about it is this could be the area under the curve y equals 2x, from -2 to 1, but this would give me -3. So that certainly can't represent area because area is never negative. So if f is always above or only touching the x-axis, in other words, if it's never negative, then the definite integral and the area are the same thing. One other thing I want to point out in terms of the notation, we saw antiderivatives, we used this notation. All right, if you recall, and we said that this was equal to f of x plus c. So I want to point out something very important. This is a class of functions. All right. In other words, these are the functions, if you include the plus c, but if you took the derivative of them, you would get little f. All right. Whereas this definite integral is a number. All right. So these are, we will see actually there's a reason we use the same notation, and we'll talk about that when we talk about the fundamental theorem of calculus. But for now, you should note that these are different things. This gives me a function or a class of functions, and this represents a number. All right. All right. Last couple examples. Getting back to this idea that if f is non-negative, then the definite integral is the area. Let's just look at a few examples. I wanted to do the definite integral from 1 to 5 of 3. All right. Now we don't necessarily need summation notation and a lot of other ways of calculating sums in order to figure this out. We can just think about it in terms of a graph. All right. Well, this is y equals 3. Right. So there's 1, 2. Here's y equals 3, and we're looking at the area from 1 to 5. So if I start at 1 here, 1, 2, 3, 4, 5. Right. So what I want to find is this area. All right. Well, clearly it's just the area of a rectangle, right? So on the width, this width here is 4. The height is 3. So this will be 12. All right. Just looking at another example like this, we could find the area from 0 to 3 of 2x plus 1 dx. All right. So again, I encourage you to draw a picture of what we're looking at here. So we know that this is a line, y-intercept of 1, and a slope of 2x. So at 1, it goes up to 3. So we're looking from 0 to 3. So at 2 and then at 3. So if I put in 1, I'm at 3. If I put in 2, I'm at 5. And if I put in 3, I'm up here at 7. So this is basically what my function looks like. And I'm looking for this area in here. All right, well, this isn't too hard, right? From 0 to 3, I have a rectangle of height 1. So this part right here is just going to equal 3. And now I have a triangle which is half of this rectangle here, right? So this goes up to, we said 7, right? So from 1 to 7, this height is 6, the width is 3, but we're only looking at half of it. So the area of the whole rectangle is 18. The area of the triangle then must be 9. So this would equal 12. Just one last example. And these are just examples of how we can use geometry to figure out these definite integrals, or these areas. So I look at from 0 to 1 of the square root of 1 minus x squared. So if y equals the square root of 1 minus x squared, then squaring both sides, we end up with y squared equals 1 minus x squared. Bringing the x squared over, we get x squared plus y squared equals 1. And that is a circle of radius 1. Alright, not very circular, but just bear with me. So that's 1, 1, negative 1, and negative 1. Alright, but when you take the square root, that's only the positive half. So we're looking at just this represents a semicircle, which is this part up here. And then we are looking at, from 0 to 1, we're just looking at this part of the semicircle right there. So we can use what we know about the area of circles. The area of a circle is pi r squared. In this case, the radius is 1, so the area of this whole circle is pi times 1 squared, which is pi. But we are just looking for the quarter of the circle that's in the first quadrant. So this would be equal to pi over 4, because this circle is centered on the origin and it's symmetric about the origin. Then each of these will be 1/4 of the area of the whole thing, or pi over 4. So this is just a way to kind of use what we know about geometry in order to compute definite integrals. And again, if we're talking about functions that are non-negative, then the definite integral and the area underneath the curve are the same thing.